In this chapter, we will be studying limits. In this lesson, we will be talking about limits, but with continuity and discontinuity in mind.
Okay, everybody. Last time we were talking about limits, and now we're going to take it the next logical step. We're going to talk about continuous functions or continuity. So again, the last thing that we said here, we were taking a look at this limit right here. The limit as x approaches 3 of x squared minus 2x. And we noticed that we could get the response or the result simply by plugging in the 3 in for the variable there. And we get the result here. So it turned out that the limit as x approaches a of this particular function was the same as f evaluated at a. This is a very significant result. And what it means here is it means that the function that we're looking at here is continuous. Now, what does continuous mean? Well, it means that the graph has no breaks or gaps in it. Okay? There's no holes in it. I can draw this graph, if you will. If I just put my cursor on it, I can draw it. I can all the way across. I never have to take my pencil off of the paper to do that, to graph it. At no point do you end up with a graph where you got to stop here, start here again, and keep going. Okay? This is a continuous graph. Now, more formally, we might say that a function is continuous at some value a, okay, if, let's take a quick look at this. First of all, the limit exists, okay? As long as the limit exists. Now, what that means specifically is approaching it from the left or the right, because remember the way a limit works. I need to be able to approach the value of a from either the left-hand side or the right-hand side in order for the limit to exist. And they have to be the same as each other. So if I approach it from the left-hand side and it starts up here again when I go from the right, well, it doesn't exist. And we're going to look at more examples of that, and you'll be able to see that a little bit more clearly. But not only that, the limit as x approaches a of f of x must be equal to f of a. Okay, so the actual value of the limit has to be the same as the value of the function at that point, at that x value, and then they'll be continuous. Now, most of the time when we have these discussions of continuity, particularly in high school or at university, when we think about this, we're comparing it to points on the graph where the function is undefined. And those are basically your non-permissible values, right? And those lead to vertical asymptotes and holes in the graph. And we've seen those before. Those are usually the sorts of things that we think about. They're not the only way that this could happen, okay? And in fact, it is possible for a function to have a problem with its continuity merely because of the way we define it. If you think back to piecewise functions from an earlier course, it is possible to piece together a couple of functions so that continuity is a problem, okay? But for the most part, when we think about issues of continuity, we're thinking about where they're undefined. Now, as a result, polynomial functions really work in our favor because polynomial functions are never undefined anywhere. Okay, that's one of their more redeeming qualities is they're defined for all real values. There's no points where there's a non-permissible value. So that means that we can use polynomials and that property of polynomials to our advantage. Because remember what we said, one of the remarks was about the limit of a function was that if you've got two functions that are equivalent at almost all of their points along the x-axis, along their domain, and they only differ at a few discrete values, well, then their limits are going to be the same. Now, what that means is every once in a while, if we've got a function that's got a problem with it, but it's equivalent to a polynomial function, well, we can use the polynomial function to get the limit. And I'm going to show you examples of that. You'll know exactly what I mean here in a bit. But for example, just to take this a little bit further here, so we know that if we've got f of x is equal to x squared minus 2x, because that's a polynomial, we know it's going to be continuous over its whole domain. So that made it all the more easy for us to conclude that if we're taking the limit as x approaches 3, that we can, in fact, just plug in the value of 3 and see what it equals. And that will be the limit of the function. Polynomials are just wonderful to work with. Okay, so let's just talk about some of the rules of continuity. Okay, so if you've got f and g, and you know that they're both continuous at a, some value a, then we know the following is true. If you take, for example, function f and just multiply it by a constant, multiplying it by a constant isn't going to change the continuity at a. So in fact, and we use this symbol right here. This upside down A means for all. Okay, so what this is saying here is that really no matter what you multiply f of x by, that product is still going to be continuous at A for all C in the real numbers. Doesn't matter what number you plug there. Additionally, if you've got those two functions that are both continuous and you add them together, well, their sum is also going to be continuous at x is equal to A, which is kind of a handy little tool. Oh, by the way, that also works for subtraction as well. If you took the difference between those two, they would also be continuous. If you take their product, then their product is also continuous at x is equal to A. The only thing we got to be careful about here is their quotient. As long as g of A does not go to 0, then their quotient is also going to be continuous at A. And if I wanted to figure out what the limit is, I would just plug in that A, okay, because I know it's going to be continuous everywhere except at its non-permissible values. And we got to pay attention to that. That's a big issue here. Now, you can't talk about continuity without also talking about a discontinuity, because they can't always be continuous here. So what's a discontinuous function? And this is one of the things I love about mathematicians. This is just a great definition. We know that continuity means that there's no gaps in the graph. Okay, there's no holes in it. Wonderful. Discontinuity means a curve that's not continuous. I love that. It's great. Okay, it's just the opposite of what we were just talking about here. And these are going to be graphs that have holes in them. Graphs that you can't draw without lifting up your pencil. Let's take a look at a couple of examples here real quick, just to see what they look like here. Here's a classic one, the reciprocal function here, 1 over x. Okay? Notice that this thing is undefined when x is equal to 0. And we've seen this before. I can draw this by riding along just below the x-axis, then I drop down here. But right at this point here, in order for me to keep drawing it, I have to pick up my pen, start up at the top here, and then go back down. So as x approaches 0 from the left of the function drops down to negative infinity. But as soon as I go to the right-hand side, if I approach 0 from the right, it goes up to infinity, positive infinity. So because these two aren't equal, the limit doesn't exist. That's a discontinuity in the graph. And we have a similar sort of thing with tangent. In fact, tangent's got a whole bunch of them. Starting at pi over 2, if you go pi to the left, pi to the left, pi to the right, you're going to bump into all of these discontinuities. And it's the same thing. Now, you'll have to forgive my graph here because it's drawing the asymptotes in for me here. But yeah, if I approach pi over 2 from the left, okay, it goes up to positive infinity. Pi over 2 from the right drops down to negative infinity. And again, there's no limit. And there's this discontinuity. There's this hole here, 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 and here. Okay, so now you get the idea that with polynomial functions, with continuous functions, to figure out the limit, all you got to do is plug in the value. That something might be a little bit weird with discontinuous functions. We're going to talk about that in a second here. But for the time being, let's just take a look at just a handful of examples of how limits might work. Okay, so let's take a look at some limits here. And for example, we've got the limit as x approaches 2 of 5x minus 1 over 2x plus 3. Now notice that this is going to be undefined when x is equal to negative 3 over 2. But that's okay, because that's not what I'm approaching. I'm approaching 2 here. So what I can do here is simply plug in, I can plug in that value of 2. That's not going to lead me into any kind of problems whatsoever here. 5 times 2 is 10, minus 1 is 9. Okay, 2 times 2 is 4, plus 3 is 7. And so my limit here was going to be 9/7. Okay, all I've got to do is plug that in. Not a problem. So that works out great here. Let's look at the next one here. The limit as k approaches negative 1 of k squared plus 1 over k plus 3. Now again, this thing is undefined at negative 3. That's not a problem. I am approaching negative 1. So the numerator and the denominator, okay, both of those polynomial functions are going to be defined at negative 1. So all I have to do is plug in the negative 1 squared, in the numerator plus 1, all over negative 1 plus 3. Negative 1 squared is 1, plus 1 is 2. Negative 1 plus 3 is 2. And so altogether we get a limit of 1. That's fantastic. Now, down here, when I plug 0 in, now, okay, notice my numerator here, 5t minus 2t squared minus t cubed, okay? The numerator here goes to 0 at 0. The denominator is this constant value of 3. Now, don't let that throw you off. That's not a big deal. It's not a problem if the numerator goes to 0. In fact, if I plug that in, I'm going to get 5 times 0 minus 2 times 0 squared minus 0 cubed. This is all over 3. Oops, there we go. All over 3. Well, that numerator is just going to be 0 minus 0 minus 0. So it's just going to be 0 over 3. Now, that's not a problem. That is 0. Okay? Perfect. But compare that to the next one here. If you take the limit as x approaches 1 of 3x squared plus 6 over x minus 1, well, notice our non-permissible value here is when x is equal to 1. Okay, now, so we do run into a little bit of an issue here, but I want to show you how you resolve this one, because it turns out in this particular case, this is not a problem. So I'm going to plug that in, okay, and I'm going to get 3 times 1 squared plus 6 all over 1 minus 1. Okay, that's going to be 3 times 1. Okay, that's going to be 9 in the numerator, and our denominator goes to 0. Now, that is undefined, okay? Division by 0 is undefined here. Now, it turns out that's okay. Therefore, we can conclude that there's no limit. Okay, the limit does not exist. My function is going to be discontinuous here, okay? We might even write here, okay, the limit. You'll often see this, DNE does not exist, okay, to represent that. That is not a problem. It's not an issue to state that the limit doesn't exist. Now, you're going to see in just a couple seconds here, there is a certain result here that we can get that's a problem. But let's just take a quick look at this. So just in summary here, if you take the limit as, let's say, x approaches a of f of x over g of x, okay, if you plug it in and you get, let's say, just because I'm approaching a here, let's just use different letters here. Let's say you get m over n, then that's your limit. That's not a problem. I'm okay with m over n. If you get 0 over n, then your limit is equal to 0. That's okay. I'm totally fine with that. And finally, if you get here m over 0, that means the limit does not exist. And again, I'm okay with that. I'm okay knowing that the limit doesn't exist. I know that there's a discontinuity, there's a hole there, there's a gap. I'm fine with that. There is one other scenario here that does pop up. What happens if you've got 0 over 0? Okay, or you will find here even infinity over infinity. Then the answer is, I don't know. And that's what we're going to look at next.
Now we will discuss indeterminate forms.
Okay, everybody, now let's take a quick look at these things called indeterminate forms. Oops, that's supposed to be an R in there. Ah, well. Okay, so when the numerator and denominator each approach different values, the limit is easy. We just took a look at that. That's when we had like m over n. Not a problem. When the numerator approaches 0 and the denominator doesn't, again, like we just said, that's not a problem. The answer is just 0. If the denominator approaches 0, but the numerator doesn't, the result is undefined. We say the limit does not exist, doesn't DNE. Again, that's not a problem. But when the numerator and the denominator both approach 0, this is an indeterminate form. And what we mean by that is that it's not clear whether a limit still exists or not, that there's something there that needs to be removed. Like normally you would look at 0 over 0 and you'd say that is definitely an undefined value. And 0 over 0 is by itself undefined, yes. But when you're talking about limits approaching that undefined, the function itself can actually behave in a very, very nice way, even though the thing that it's pointing to is undefined like that. And as a result, okay, there might still be a limit of this function here, but what you might have to do is we might have to simplify this thing a little bit, which means adding or subtracting fractions. Okay, you're going to see that pop up, factoring, or rationalizing the function first. Okay, you're often going to see that you're going to have to do one of those things to make it work. Now let's. Okay, so now let's take a look at some examples of functions that end up being, functions that end up being indeterminate and how you deal with the limits of those things here. So we've got the limit as x approaches 2 of x squared minus 4 over x minus 2. Now, if you plug in 2 into this, you're going to get 2 squared minus 4, 0, over 2 minus 2 is 0. So we get 0 over 0. Now, the thing to do in a case like this, and we were talking about this before here, there's a few things that you can do to approach this, but we want to simplify this. So often, one of the very first things that we're going to do here is we're going to factor. Now, that numerator, okay, is a difference of squares. So we get x minus 2 times x plus 2 all over x minus 2. Now, notice that I've got a common factor of x minus 2 over x minus 2. Now, that can be simplified. I can actually divide that out. X minus 2 divided by x minus 2 is 1. Now, that's true everywhere so long as we do not allow x to equal the value 2, because that would be undefined. However, in my function here, in my limit here, I'm only ever approaching 2. I never actually get to 2. So I never actually get to the undefined value. That was one of the beautiful things about this, okay, is that I never actually got to that value that we're approaching. So that non-permissible is never actually even an issue. So this actually becomes x plus 2. Now, notice that these two functions here and here, okay, x minus 2 times x plus 2 over x minus 2 and x plus 2, they are equivalent. They are similar at every value of x except for when x is equal to 2. Now I've rewritten that expression in terms of a polynomial that is equivalent to it almost everywhere. And now if I take and just plug that 2 in, I get 2 plus 2, and I get a limit of 4. That's the limit of the original function. And I got it by finding a polynomial function that was equivalent to the original. That's what I was trying to talk about. I was trying to get at before when we were discussing this. Okay. Now, a couple things that I want you to notice here. I want you to notice that I stopped writing the limit when I got to here, when I actually plugged in, okay, when I actually plugged in the limit right here, when I took it. Oftentimes people either stop writing that limit as x approaches 2, they stop writing it too early, or they just keep writing it all the way down here. As soon as you do the substitution, you're done. So don't do that anymore. Another thing that I think would be interesting to look at here is what it is that we're actually seeing. And if we take a quick look at the graph here, okay, what's happening here is we've got this x plus 2. That function looks like this. But once you get to 2, turns out there's a little hole in it. Now, you should have seen this in a previous course. Okay, when you get to 2 here, there's this hole in it. And as you approach that hole from the left, approach it from the right, we're getting a y value here of 4. Okay, that's the y value of the hole, but the point does not exist there. That, however, does not affect the presence of the limit. The limit is pointing at the point that should be there, that or not should be there, that's where the graph is kind of pointing to, leading you to. So just be aware that that's how that works. Okay, let's take a look at another one. We're going to take the limit. Let's make it r this time, as r approaches 0 of 3r squared plus 7r over 4r. Similar sort of thing is occurring here. If you plug in 0, you're going to get 0 over 0, and that's an indeterminate form. So similar to what we just did, we're going to factor out the numerator first. We get 3r plus 7 over 4r. Just like before, the r's will cancel. Whoops, and I just did what I told you not to do. I can't believe I did that. This is still the limit as r approaches 0. Now I can cancel those r's, so this is still the limit as r approaches 0. Don't forget to write that. That was crazy that I did that. Now I can cancel those r's out so long as r does not equal 0, but it won't equal 0. I'm only approaching it. And now if you plug in the 0, and now I don't have to write this anymore because I'm going to evaluate that expression at 0. 3 times 0 is 0 plus 7 is 7 over 4. Okay, now in both of these cases here, okay, I factored, okay, I factored and canceled. Now, when you've got that, when you can do that and find the limit here, that little bit that we canceled here, that hole that we get in that graph, that's called a removable, okay, a removable discontinuity. Okay, a removable discontinuity. Anyway, just a little bit of vocabulary there. Now, let's keep going here. Let's take a look at another one. 3. Okay, I'm gonna have to clear the graph here for a second. Just give me one moment here. Okay, let's do 3. And this time let's take the limit as x approaches negative 3. And this time I've got 1 over x plus 1 over 3 all over x plus 3. Okay, now to evaluate this one, and I had mentioned that this might be an issue before here, I've got fractions in the numerator. So one of the things that you might have to do to evaluate a limit is add those fractions. Now I know that the denominator is going to be 3x, and so I'm going to get 3 plus x, and then down in the denominator x plus 3. Okay, so I added together the fractions in the numerator, and now I'm going to do that division. This is like divided by x plus 3. And if you take the limit as x approaches negative 3, you're going to get 3 plus x over 3x. And then we're going to multiply by the reciprocal of the denominator. Because remember, that's how we do that. Now, the x plus 3 is going to cancel. Okay, or at least I'm going to divide those out and get that 1. And that's true as long as x does not equal negative 3. But I never get there. So here's another example of a kind of removable discontinuity. I'm going to get the limit as x approaches negative 3 of 1 over 3x. And now I can just plug in that negative 3 and I get 1 over, or actually negative 1 over 9. Okay? And that's my limit. Now, one more. 4. This is going to be the limit as x approaches 1. Okay, x approaches 1. And we're going to make this the square root of x plus 8 minus 3 all over x minus 1. Now, if you let x go to 1 here, 1 plus 8 is 9, square root of 9 is 3, minus 3 is 0, and the denominator goes to 0. The way you handle this one is to rationalize. When you see that square root in there with that limit, what we want to do is we want to rationalize this. And this is why you learned rationalizing so long ago. Okay? This is where it really becomes useful. So we're going to multiply numerator and denominator by that binomial conjugate. Okay. Now, when you multiply that out in the numerator, we're going to get x plus 8 in the numerator. And then we know that the middle terms, when you expand that out, are going to cancel. We're going to get minus 9 up there. Now, in the denominator, I'm not even going to bother expanding that out. Okay, I'm just going to write it like this. And you'll see why in a second here, why it's not even necessary to expand that out. Now, we're going to take the limit as x approaches 1. X plus 8 minus 9 is the same as x minus 1. And then in the denominator, look at that. We got that factor of x minus 1 there. And we got this x square root of x plus 3, 8 and all plus 3. Now, notice the x minus 1s are going to cancel as long as x does not equal 1. Now, you would not have seen those two factors canceling if you had expanded that out here. But now what we can do here is we can just plug in the 1, and we're going to get 1 over, and if you plug in into the denominator, we're going to get, we're going to get 6 there. It's going to get 1 over 6 when we plug in that value. And that's how you evaluate that limit.
And to finish, we'll just discuss the basic properties of limits.
Okay, everybody, just to finish this off here, we're just going to discuss some basic properties of limits. Okay, first of all, the limit of a constant times a function is the constant times the limit of the function. So in other words, having that, I'm going to I'm gonna turn on my little laser pointer here. So having that constant out front inside the limit is the same as pulling that limit, that c out front of the limit. Okay, that's an important concept that you're going to see that come up later in the course, particularly near the end when we start talking about something called integrals. It's going to affect our rules for derivatives when we get to there, but you're going to see that pop up with integrals as well. Kind of a neat little tool. The limit of the sum or difference is the sum or difference of the limits. In other words, you can either add or subtract first, or take the limits and then add and subtract the limits. That should work. That shouldn't be a problem at all. The limit of a product is the product of the limits. Same sort of thing. You can multiply first, or take the limits then multiply. The limit of a quotient is the quotient of the limits. Same sort of thing, with the stipulation once again that g of x can't go to 0. If you've got a power, okay, the power of the limit, sorry, the limit of the power is the same as the power of the limit, so you can either use that exponent before or after. And because of the relationship between powers and roots, you can actually do the same thing here down with roots. So either you can take the nth root of the function and then take the limit of that, or take the limit of the function and take the nth root of the limit. It doesn't really matter which order you do that in, and you're going to see how these sorts of ideas of limits useful in this chapter for sure. But when we move on to our next chapter on derivatives, you'll see how these limit rules become rules for derivatives, or influence the rules for derivatives as well.